Hello, everybody. Thank you so much for joining us this afternoon for our webinar on M-STEP Science Prep, 3D item analysis and strategies for student readiness. We are so excited to get started. Thank you to those of you who've started introducing yourselves in the chat. It's always nice just to see who's here and where they're from and what they're doing. And as promised, we will go ahead and introduce ourselves. So my name is Emily Miller. My pronouns are she, her. Prior to Inner Orbit, I was a high school chemistry teacher for 10 years in Minnesota. I taught in our alternative learning program. I taught regular chem, honors chem, so lots of different ways to teach a lot of different kids. I worked a lot with the NGSS within my time in the classroom. I also got to be a PLC lead, so I got to do a lot of data-driven dialogue. And now I get to partner with districts to help them implement Inner Orbit. And I think this is really important for you to know about me. I've watched all the Star Wars movies, especially the original trilogy, like a million times. And obviously, this is scientifically accurate because we are science people. So, and we've got our colleague Julia here. She's just going to be hanging out in the chat, answering any questions that you all might have. And I'm going to go ahead and now pass it over to my colleague Daniel.
Hey everyone, my name is Daniel Jackson. I was formerly a curriculum director, high school and middle school science teacher for 11 years in education. I taught at an international school in Colombia. I was a global education and Fulbright TGC scholar in Morocco, and I currently partner with school leaders and teachers new to Inner Orbit. And regarding Star Wars, I am fully aware of how deep it is in society and culture, but I've only seen the movies once and nothing pulled me back to see them again. So if we see some Star Wars things, it's probably Emily that put them in there. But I do want to go over the agenda of what we will cover today. Our goal is to cover the structure and expectations of the M-STEP science test, be able to identify the NGSS dimensions within science test items, and learn how scaffolded formative assessments can support student progression towards confidently answering 3D phenomena-driven questions. We'll be together for about 45 minutes. First, I'll give an overview of Inner Orbit. Next, we'll cover the shift to sense making and talk through assessments that align with the NSTEP science test. From there, we'll go over the M-STEP structure along with an item analysis and examples of scaffolded formatives from Inner Orbit that can help teachers prepare students for these exams. We will also provide a helpful classroom resource for phenomenon-based questions towards the end. And as the wise Yoda once said, do or do not, there is no try. So let's get this webinar started. All right, I'll begin with a quick introduction to what Inner Orbit is and how it supports educators. At Inner Orbit, we like to say there are three core components to what we do. We have phenomena, we have assessments, and we have detailed reports. Our high integrity 3D assessments at Inner Orbit are designed to provide those meaningful and actionable student data so that educators can make informed instructional decisions with confidence. We also make the NGSS accessible for both you and your students through innovative approaches to sense making. That means we don't just drop students straight into these complex 3D questions. Instead, we use scaffolded prompts that move students from more basic, one-dimensional content-focused understanding towards those larger three-dimensional questions, which we'll talk about in just a bit. In addition to the questions themselves, we also provide supporting activities you can use with your students to help build that understanding over time. So they're prepared and confident when they reach those more rigorous summative assessments later on, such as on the M-STEP. We also provide guidance, supporting resources, and professional development to help you reach your NGSS goals, just like the session we're hosting today. There will be a link dropped in the chat in just a moment. If you're interested in learning more about Inner Orbit, feel free to fill out the interest form, and from there, we'll share additional information, show you how you can try Inner Orbit yourself within your districts. Next, I want to talk about the shift to sense making in regards to how we can interpret proficiency when prepping for the M-STEP. If you've been teaching for years, you probably felt this huge shift already. Proficiency has moved from those standards that often focused on isolated facts, content, or skills to performance expectations that describe what students should actually be doing to demonstrate understanding. Under the NGSS, proficiency is defined by sense making, which is when students integrate the three dimensions to explain phenomena or solve problems, not just recall the information. Let's now take a look at what those three dimensions of the NGSS are. As you may know, the three dimensions are what sit at the heart of the NGSS. First, we have the disciplinary core ideas. These are the content the science that students are learning. In this example, the DCI we're focusing on is adaptation. Students need to understand that in a given habitat, some organisms survive well, some survive less well, and some cannot survive at all. That understanding is a critical part of the content students are expected to learn, although on its own, that kind of recall is no longer sufficient to say a student is proficient. The second dimension is the science and engineering practices. This is what students are actually doing with the science. Practices include things like constructing arguments, analyzing data, and developing or using models. In other words, thinking and acting like scientists. In this performance expectation, students are expected to engage in an argument from evidence, meaning they must construct a claim and support it with evidence based on what they already learned about adaptation. And finally, we have the cross-cutting concepts. These are the big ideas that are connected across scientific disciplines. They shape how students think about science. Examples include patterns, systems, and cause and effect. In the example here, the cross-cutting concept is cause and effect. Students need to reason through how certain traits or conditions in a habitat cause some organisms to survive better than others. When all three of these dimensions come together, we get a much clearer picture of what the students truly understand. We're no longer just measuring what they can memorize, we're assessing how they think, reason, and apply their knowledge. And that's a key difference with three-dimensional sense-making focused assessments. Next, let's talk a little bit more about sense-making. So when we say sense-making, we're talking about what happens when students pull together everything they already know, their ideas, their skills, and their experiences to make sense of something they don't fully understand yet. That process usually begins with a phenomena that's puzzling and raises questions. From there, students might use science and engineering practices to investigate. Maybe they ask questions, analyze data, or construct explanations, while at the same time drawing on disciplinary core ideas and the cross-cutting concepts. And as we see in the image, sense making isn't meant to be linear. Students won't always move step by step in a straight line. Instead, they can move back and forth between practices, content, and cross-cutting concepts as they refine their understanding. Rather than jumping straight to the right answer, they're working to figure out why something is happening. They're testing ideas, revising their thinking, and asking better questions along the way. That's really what the NGSS is aiming for, and what we believe strong assessments and strongest instruction should be designed to support. Students that show proficiency are able to bring all these pieces together to make sense of new or novel scenarios. Now that we've gone over sense making, I'll pass it over to Emily to show you how sense making is incorporated into the M step.
Thank you so much, Daniel. So let's actually dive in and see how these three dimensions and sense making, like Daniel mentioned, actually are incorporated into that M-STEP science test. So the first thing I want to talk about is just the overall structure of the M-STEP. So as you may know, the M-STEP is given at 5th grade, 8th grade, and 11th grade. So at the 5th grade level, students will have about an hour and a half to complete the science section of the M-STEP. As you can see, they're also going to be doing ELA, math, and social studies as well. But they're going to have an hour and a half for that specific science portion. For 8th grade, students are also going to have an hour and a half for that science portion. They are again going to be looking at some ELA and math and social studies too while doing the M-STEP. And then for 11th grade, they will again have that hour and a half in order to take the science portion. How the actual M-STEP is going to look, the M-STEP science, excuse me, is there's going to be 7 different clusters on the M-STEP science portion. These clusters are all going to be centered around the same phenomena. So there's going to be multiple questions that students are going to need to continuously refer back to the same real world situation or phenomena in order to answer the questions. For these phenomena clusters, there's going to be at least 2 that are life science, another 2 that are earth and space science, and 2 that are physical science. The 7th one is going to be a field test item. Generally, field test items do not actually factor into the student's overall score. They're trying to gather some initial data and understanding in order to help further develop future tests. With these different phenomena clusters, each one is going to be a bundle of similar performance expectations. So for example, where it says physical science 1 here, it's going to be a bundle of physical science performance expectations that are all about the same general concept, or idea. To show you a little bit more of an in-depth example of what this looks like, here is a list of some of the middle school 8th grade physical science bundles. So we've got structure and properties of matter, which is a bundle of 4 PEs, chemical reactions, which is a bundle of 5, etc. Then what they're going to do is they're then going to write items based off of those performance expectations, and all of those items are going to reference the same phenomena. So they're going to pick one real world example. All the items will tie back to it, and all of these items are going to assess the different PEs within the bundle. Now, the way that they're going to break it down is they're going to make sure that each DCI and each performance expectation, each SEP, and each CCC is assessed at least once throughout the different items. This also means that items are going to be either two-dimensional, so incorporate the DCI and SEP or the DCI and the CCC, or they'll be three-dimensional and incorporate all 3 dimensions. So we've got a nice little picture graph here. So one of the topic bundles is energy, which is a bundle of 5 different physical science PEs. You can see those 5 different PEs listed here. Now, each one of these PEs has a DCI, an SEP, and a CCC a part of it. These are all now going to be assessed within the same cluster with the same phenomena. So the first question is a two-dimensional question looking at the DCI from PS3A and SEP number 2. The second item is also two-dimensional. It's looking at a DCI and a CCC. The third item is three-dimensional, two-dimensional, two-dimensional, and three-dimensional. So they're going to be pulling different SEPs and different CCCs and different DCIs from that PE bundle and writing questions to make sure everything is hit at least once. I am going to show you a little bit more exactly what that looks like here in a chemical reactions physical science bundle. So in this bundle of chemical reactions PEs, there are 3 different PEs that are a part of the bundle: MSPS12, MSPS15, and MSPS16. Down here, you can see the 3 different SEPs that are incorporated within those 3 PEs, the different DCIs, and then the different CCCs. Over here is a roadmap of how those DCIs, SEPs, and CCCs are mapped out within this cluster about hand warmers. So over here, you can see what DCI is being assessed in each of the questions. You can see what SEP is being asked in each of the questions and which CCC. If it says NA, like the one down here, the CCC is not being assessed, and this would just be a two-dimensional question. So the big takeaway that I want you all to take from here is that students are going to be asked either two-dimensional or three-dimensional questions. So when helping prepare students for the M-STEP science test, we need to make sure that we're giving them exposure to SEPs and CCCs and going beyond just DCI level content only questions. Now, the last thing I wanted to talk about in terms of the M-STEP science is what we can consider to be proficient when it comes to measuring for success on the M-STEP science. Now, generally speaking, the goal is to get to a level 3. That means your students are proficient. But at least for me, when I'm looking at all these numbers here, I have a hard time getting a good frame of reference on what level we're trying to get to be proficient. So at InterOrbit, we've done something what we call cut scores to try to help put this more in a traditional classroom teacher lens. So for the 5th grade test, the minimum amount of points a student can earn is a 1424, and the maximum is a 1573. For 8th grade, 1728, 1876, 2036, 2177. Don't worry, I did the math for you. So the amount of points that are possible to be earned on the 5th grade test looks to be 149, 148 for the 8th grade, and 141 for the 11th grade. Now let's look at that level 3 proficient column. In order to get a proficient on the 5th grade test, students have to earn at least 1500, 1800 for 8th grade, and 2100 for 11th grade. Again, don't worry, I did the math for you. For the 5th grade exam, that means that you need to earn about 76 of the points, grade 8, 72, grade 11, 64. Now you might see where I'm going with this. So if students need to get about 76 points on the fifth grade test, and there's 149 points available, that's about 51% of the points. For grade 8, it's about 49%. For grade 11, it is about 45%. So what does this mean? When we're looking at the amount of points that students can earn on these different exams, we're looking at proficiency being around 51, 49 to 45%. Now, I don't know about you, but my classroom teacher brain is programmed to look at those percentages and think, if, like we are failing, this is not so hot. And while this is a more simplified version to actually look into the scoring and the mechanisms behind the M-Step science, I think it does give a really nice frame of reference for us as teachers. Because if we are assessing students with this rigorous three-dimensional expectation, that traditional 90, 80, 70 that we kind of been programmed to run our classrooms on isn't necessarily comparable to the proficiency levels that we're expecting students to complete on the statewide assessment. So when you're giving students these rigorous phenomena-based three-dimensional, two-dimensional items, if they're getting about more than half of them right, they actually might be on track to nearing that proficiency that we're looking for on that M-Step science. So this is just kind of a way to give you a nice shift of focus when you are giving your students these types of questions to actually see if they may or may not be ready for the test. So now that we've got a little bit better idea of how the M-Step is structured, how they organize the phenomena clusters, what types of items are going to be asked, I actually want to do a deep dive into an actual 8th grade M-Step science item so we can actually see how it is three-dimensional. And then from there, we can talk about how we could scaffold students to be able to answer the three-dimensional question we're about to look at. So this particular question that I'm about to show you is assessing MSPS 1-5. Now, if you remember, the phenomena clusters are on PE bundles. So there's a bunch of PEs that they've bundled together and they're going to try to hit each dimension in each one. This particular question hits the SCP, the DCI, and the CCC, all from MSPS 1-5. And I'm going to show you that here on this little answer key. So we're looking at question 3. There is a part A and a part B and a part C. And the DCI is PS1B, which is all about chemical reactions. The SCP is SCP number 2, which is developing and using models. And the cross-cutting concept is cross-cutting concept number 5, which is energy and matter. All of this comes together to give us the MSPS 1-5 PE, which is develop and use a model, SCP, to describe how the total number of atoms does not change in a chemical reaction, DCI, and thus mass is conserved, CCC. So let's go ahead and see how all of these different dimensions actually play out into this item. The first thing I want to show you is the phenomena that students will be referencing. Remember, all of these questions are going to be centered around a novel phenomena. So students are going to need to have to interact with this in order to answer the question. And this one's all about hand warmers. To save you the time for reading, essentially, students are curious how hand warmers work, and they're curious to see if the material inside the hand warmer works better or differently when it's outside of the actual hand warmer package. So students actually go ahead and remove some of the material within the hand warmer, and then they collect some data on how it looks initially when they remove it from the hand warmer bag, and then what it looks like afterwards. So with this, here is that question that we were just talking about that aligns to MSPS 1-5. This question has 2 parts. The students decide to develop a model to explain why the iron appeared to change overnight. To complete the model, the students need to include iron atoms from the hand warmer, oxygen atoms from the air, the final substance they observed. Part A, complete the student model by dragging the appropriate number of atoms from the key into the model. So we have the final substance modeled here, and students need to drag the iron and the oxygen into the initial iron atoms and then into the initial oxygen in the air part. That's the first part. The second part is select one limitation of the model shown in part A. I got a bad feeling about this one, Chewy. This is a lot. We're asking students to interact with a phenomena about hand warmers and do a lot of reading, and then we're asking them to translate what they just learned into a model of a chemical reaction, and then not only complete the model, but then think about what limitations the model we just created may have. It's a lot, but we have a way to scaffold students up to this. So the first thing we're going to do is we're going to pick apart how the three dimensions play into this problem. And then from there, we'll talk about how we can scaffold students to do all those dimensions together. So let's look back at part A and part B of this question, and let's quick remind ourselves of the three dimensions at play. So the SEP is developing and using models. The DCI is all about chemical reactions, and the CCC is energy and matter. So first of all, let's see if we can see how the SEP is taking a play into this problem, developing and using models. And this question is a little obvious because students need to complete the student model in order to go ahead and get this question right. So they need to physically create a model by manipulating the different atoms and putting them in the right space. Also, they're being asked to kind of take a step further and then think about limitations of this model. Because specifically here, you can see it has students developing a model to describe unobservable mechanisms. So we can't physically see the oxygen and the iron atoms changing and moving around in this chemical reaction. So this model is helping us try to imagine what is going on at that microscopic scale. But all good models have limitations, so they're asking students to think about what that might be as well. So that is the SEP level of this question. Now let's see how the DCI is incorporated into the question. This DCI is all about chemical reactions. So understanding that atoms can rearrange into new molecules or into new elements, and that those new molecules and elements could have different properties from what they had previously. So this kind of comes into, at least for me, into part B here, where it shows the model does not show how the atoms are organized in the final substance. So this is not the correct answer because it does show how they're organized differently. So one of the key things that we would be looking for in a correct student response is when they're drawing the iron and the oxygen atoms initially, that they are not arranged in the order that they are in that final substance. So they shouldn't have the 2 irons and the 3 oxygens all connecting within a molecule. Because in the table over here, we can see that they have different properties. So in order for the iron and the oxygen to have different properties, those atoms need to be rearranged differently. So that is not a limitation. So if students have that conceptual understanding, if they have that content understanding of atoms rearranging to make new things with new properties, they should be able to know not to select answer C. Now for the last dimension, the cross-cutting concept, which is all about energy and matter, and more specifically how matter is conserved because atoms are conserved during a chemical reaction. So in order to get this one right, students should be counting how many atoms are placed in the final substance and make sure they have the same number of atoms on the reactant side. So if there's 4 irons to begin with, they need to start with 4 irons. If there's 6 oxygens at the end, they need to start with those 6 oxygens. So that is not a limit of the model. We can see the conservation of mass if drawn correctly. So again, if we have this ability to eliminate answer choice A and C because of our DCI knowledge and our CCC understanding, then we should be able to pick the right answer, which would be option B. Again, that's a lot. We're asking students to think a lot, and this is just one question. This is one question on one phenomena cluster. There's 6 other clusters that all have anywhere from 5 to 8 questions. It's a lot. But like I said, I'm going to talk you through a way we can help students scaffold up to that. But before we do, just a quick review. The grades 5 and 8 tests are administered in 2 sessions. Grade 11 is 1. There's going to be 7 phenomena clusters. 2 life science, 2 physical science, 2 earth and space science, and then 1 field test cluster. And then each cluster is going to be a bundle of PEs that are all about the same phenomena. All of the SCPs and CCCs and DCIs are going to be assessed, so items are going to either be 2D or 3D. So it is crucial that we are asking students 2D and 3D questions ahead of the test to make sure they have that practice with SCPs and CCCs. And also keep in mind that that proficiency is around that 50-ish%. So when you are asking students questions like these, just remember that the bar is a little bit different than what we traditionally expect. So I keep talking about how we can get there. Let's do it. So, really, like Daniel mentioned at the beginning, there's been this big shift in science education from going to just teaching students content to getting them to have this three-dimensional understanding of science. But as Han Solo said, never tell me the odds. We can totally do this Kessel run in 12 parsecs as long as we scaffold students step by step to get to that three-dimensional understanding. So, how we tackle this at Inner Orbit is we've written different types of questions in order to eventually get to that three-dimensional understanding. So, the first type of question that you're going to see on our site are one-dimensional DCI only questions. So, these are kind of your typical, like, what is the powerhouse of the cell type of questions. Now, we need to move beyond these types of questions, but it's also important that students know the content. So they still need to understand atoms and molecules and the difference between those definitions before we can dive in deeper. So the one-dimensional questions ensure our students understand the content before we start to add other layers to them, which we do in our two-dimensional questions. Two-dimensional questions still have the DCI component, but now we layer in either the cross-cutting concept or the SEP on top. Now we do this so students have a chance to flex and practice those skills individually. And two, it yields really interesting data to see which dimensions students may need more support with before we get to three-dimensional questions, which is our ultimate goal. Because if students can do all three dimensions with a novel phenomena, they're demonstrating that proficiency with that PE. So, keeping this scaffolding structure in mind of 1D, 2D to 3D, I want to show you a scaffolded formative assessment that we have on Inner Orbit that models the same progression. The performance expectation we're going to be looking at is the exact same performance expectation that we looked at with that M-STEP sample. So the MSPS15. So all about developing and using models with chemical reactions and understanding that matter is conserved. The phenomena we have on Inner Orbit, one of the phenomena we have on Inner Orbit to help with this, is talking about bikes rusting. So understanding that if you leave bikes out, that over time they can get this rustiness to them. So what's going on with that? So again, remember our DCI is chemical reactions, SEP is developing and using models, and the CCC is energy and matter. So I have a question for you all. The first question on this scaffolded formative example is which of the following best describes the parts of one rust particle, Fe2O3? So I want y'all to answer in the chat. Do you think this question is one-dimensional, two-dimensional, or three-dimensional? This question is one-dimensional. What we're asking students to do here is we're asking them to kind of understand the difference between atoms and bonding and molecules so they can look at that chemical formula of Fe2O3 and understand the information that it's telling us, which is kind of that like content knowledge there. So here we're just making sure students understand the core content before we start to dive a little bit deeper. So the next question on the scaffolded formative is this. Which of the following is true regarding the conservation of matter in chemical and physical processes? So what do y'all think? Is this one-dimensional, two-dimensional, or three-dimensional? The answer here is two-dimensional. We're really trying to get at that CCC, that cross-cutting concept understanding of energy and matter and the fact that matter is conserved. So again, before we go much deeper, we want to make sure that they understand that overarching idea of conservation of matter before we start to add in those other layers to it. Another question we have on this, refer to figure 2, which model best shows the reaction of oxygen and iron to create iron oxide? So what do y'all think? Is this 1D, 2D, or 3D? This is 2D. The word model might have tipped you off. So we're asking students to look at the different student models of Fe2O3 forming and comparing it to the chemical reaction. And so seeing which one of these models best represents this unobservable mechanism of this chemical reaction. Another question, refer to figure 2, which of the following models does not show conservation of mass? What do y'all think? Is this question one-dimensional, two-dimensional, or three-dimensional? It is three-dimensional. I really like this question because I think it's really easy to pick apart the different dimensions at play. Because first, we're looking at this idea of chemical reactions, right? So they have to understand the difference between atoms and molecules. We're asking them to look at the models. So we're asking them to look at these different representations of this chemical reaction. And we're specifically asking them to look through the lens of conservation of matter. So which one of these does not show that matter is conserved? So students need to incorporate all three dimensions in order to successfully answer this question. And on inner orbit, we can even take this a step farther, similar to how that M-step question was as well. Cameron developed this model to answer the question, how does a bike get rusty and where does the orange color come from? She used yellow for oxygen atoms and red for iron atoms because when you mix yellow and red, it makes orange. Use what you know about chemical reactions to help Cameron improve her model. In your response, explain why rust forms, describe how the properties of rust are different from the original properties, and provide suggestions on how to revise her model. This is another three-dimensional question, but this one has a lot less scaffolding than the other one. Because in this case, we're asking students in their own words to describe the chemical reaction of rust, so using their content knowledge to look at that chemical reaction and explain why it occurs. Also understanding that different atoms and elements and molecules have different properties. And we're also asking them to look to her model and help revise it at the same time. So to kind of bring us back all the way to the beginning here, at first, we asked students a one-dimensional question, so just making sure that they understood the foundations of chemical reactions and atoms and molecules. Then from there, we asked them two different questions. One, trying to see if they understood the idea of the law of conservation of matter, and two, asking them to look at different student models in order to see which one of those best reflected the chemical reaction at hand. Then we asked them a question which lumped those two ideas together. So which model is looking at the idea of conservation of mass? And then from there, we can ask students to go even farther and take out more scaffolding and have them look at a model, give revisions, and actually explain what's going on within it. This is our idea of scaffolding towards sense making. By being able to have students answer questions in this progression, one, you're giving students the scaffolding to eventually answer a more rigorous question like the one at the bottom. And two, on our site, you get really informative data along the way. And I'm going to not, even though I'm so excited about it, I'm going to let Daniel talk about that a little bit more in depth in just a sec. But first, I want to show you how you could find and create your own scaffolded formative assessment on inner orbit if you're interested. So on our site, let's say you're teaching the 8th grade Amplify curriculum and you're on your natural selection unit and you're wrapping up the standard MSLS 4.6. You can go on our site and we actually have curriculum alignment guides. Now, you don't have to be using one of these curriculum in order to use our site, but if you happen to, it can make navigating a little bit easier because you can go ahead and click Amplify. You can click your natural selection unit that you're on. You can click Formative, and right there, you'll find one of these pre-made scaffolded formative assessments ready to go that have that progression of 1D, 2D to 3D. So you can give students scaffolding along the way in order to answer that three-dimensional question and give you informative data on where they may need more support. If this is something that may be potentially interesting to you and your team, my colleague Julia is going to go ahead and drop in the chat an interest form. This is not like a super big commitment or anything like that. This is just you letting us know that you might be interested in learning more and you might be interested in trying this out for free to see if this is something that aligns with what you and your team may want in the future. Now with that, I keep talking about all this awesome data. So I'm going to go ahead and pass it over to Daniel so he can give us a little bit more insights into what that can look like.
Thanks, Emily. Well, as we know in science, data is everything. So let's take a look at the data and how it can look, the insights can look when you provide an assessment on inner orbit, excuse me. Because all inner orbit summative assessments are 2 or 3-dimensional, just like on the M-STEP science test, every question includes either a science and engineering practice, a cross-cutting concept, or both. This allows teachers and admins to look beyond missed standards and to actually identify patterns across students, classrooms, and schools. The dimensions report here provides this insight by showing performance across the specific elements of each of the three dimensions and allowing you to drill down by class, grade level, or school. This helps you target instruction, support learning across multiple performance expectations, and better align your preparations to state assessments like the M-STEP science test. Now let's zoom out to a district level view. This is one of my favorite reports because it really highlights why looking at the science and engineering practices and cross-cutting concepts is so powerful. Across the top, you can see different dimensions, and down the side, you have the different schools of the district, and in the table, you see the performance across the district. In this example, you can quickly see differences between schools, such as School 2 struggling with the SEP of constructing explanations and designing solutions, while School 5 is performing much better in that same area. That easy contrast opens the door for meaningful collaboration, allowing educators to ask what's working in one school and how those strategies can be shared across the district. Now let's zoom into the teacher level view and look at student performance on individual questions. So in this example, we can see that students tend to do well on the 1D DCI only question and continue to perform strongly on the 2D question where a cross-cutting concept is added. However, we begin to see a drop when the SEP is introduced on the other 2D question, and an even larger drop when all three dimensions are included in the last question. Because that same SEP appears on both the 2D and 3D questions, we can identify that as a key area where students need more targeted support, rather than unnecessarily reviewing the DCI that they're already doing well on. That's the real power of this data. It helps us move beyond just what students missed to focusing on why it was missed, so that instruction can be adjusted with intention. While assessment is a crucial component in helping students prepare for the M-STEP science test, Inner Orbit also has created some informal sense-making activities to help students practice. I wanted to share one of those activities with you called the Science Talks that helps you target these supports in the classroom and can be implemented right away. In the Science Talks activity, students engage in a facilitated discussion around a novel phenomena, exploring questions, sharing ideas, and collaboratively building understanding. Teachers will select a phenomenon from our library, and students work together to unpack it using all three dimensions, while they collaborate to highlight the bigger patterns or relationships they notice. It's important to note that this activity is a scaffolded support and not another test. So once teachers see the data that shows students are struggling with 3D questions, the next steps could be to provide this type of instruction and support in the classroom. And teachers can run science talks at any point of the year to help students become more comfortable making sense of phenomena out loud. By practicing this way, when students encounter a 3D question on an assessment like the M-STEP, it doesn't feel like an entirely new task. Instead, it's the same kind of thinking they've been practicing in class. These science talks promote collaborative sense making and help students ask better questions and connect their prior knowledge to new concepts as they get prepared for the M-STEP science test. This can be a great informal first step for test prep that can be implemented right away. All right, that's all we have planned for today. I'm going to pass it off to Emily to wrap up the webinar.
Awesome. Thank you, Danielle. So I just want to recap some of the major things that we talked about here today before leaving you. So we came here today to talk about the structure and expectations of the M-STEP science test, talk about how the NGSS dimensions are within those test items, and how we can scaffold students to answer questions at that three-dimensional rigor. Remember, on the test, students are going to be asked those 2D and 3D questions. So in helping students prepare for the M-STEP science test, we want to make sure that we're giving them practice with the SCPs and the CCCs within those 2D and 3D questions, so they're used to questions that are like that. Another thing to keep in mind too is proficiency is more about that 50-ish%. So if you still kind of have that framework of like 90, 80, 70, it might be nice to know when you're giving students questions at this rigor, we're not holding them to the same classroom expectations that we generally do. All right, with that being said, my colleague Julia is going to once again drop the interest form in the chat. Again, this is not any commitment or anything. This is just letting us know that you are interested in learning more, and we'll give you some more information about Inner Orbit as well as some potential next steps about how you could go ahead and try it out within your classroom or within your district. We post videos like this all the time in our YouTube channel at Inner Orbit NGSS. And if you've got any questions or if you want to follow up with us, you can email at us at inquiries@innerorbit.com at any point. And as the great Han Solo said, and all the other Jedi. May the Force be with you. Thank you so much again for joining us this afternoon. If you have any questions, please reach out or fill out the interest form, and we hope to see you all again soon. Thank you so much.